Okay, here we go. Properties of gases. Now, from your guided reading, you should know the kinetic molecular theory. What does that mean? That means stuff that you kind of know already, but let's just talk about it because it's on the PowerPoint. Number one, gases are made up of tiny particles. No kidding. Number two, gases have no definite shape or definite volume, which is what my little guy is learning in his science class. Gas particles move rapidly in random motion, which makes sense. They're moving around. Gas particles constantly collide with each other and other objects. That also makes sense. And gases are not attracted to one another, they're just bouncing around. Okay. Oh, by the way, most of these are right. One of them is an assumption. Gas pressure. Gas pressure is the result of simultaneous collisions of billions of gas particles with the walls of a container. So the gas is going boing, 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 boing. And if we were in class, I'd get out my little container with my little rubber balls in it and bounce it around for you. So you would see air pressure. But of course, we don't have it, so maybe I'll videotape it for you later. Okay. What is a vacuum? Is that what helps you clean the house? Kind of. But a science vacuum is when there's no gas particles present, like in outer space, like those dudes who just went up to the International Space Station. So there's no gas in a vacuum, which means there's no pressure in the vacuum. And of course, if we were in school, you'd see one of these, and I'd show you a whole bunch of cool demonstrations, which are very cool. Okay, so how do we talk about pressure? Let's talk about air pressure. Air pressure is measured using a barometer, and here's our barometer here. The air pressure pushes down on it, pushes up this mercury to 760 millimeters, which is a little under a meter. Okay, that's for standard temperature and pressure. So, what is standard temperature pressure? It's the pressure it's standard at 1 atmosphere at sea level. So, 1 atmosphere is the air pressure. Now, it's also can be measured in millimeters of mercury. Sometimes you'll see it this way, and sometimes you'll see it as a kPa or kilopascal. And for you folks who are into car tire stuff, that is, if you get your car and you fill your tire with about 32 to 35 psi, which is pounds per square inch, which is a pressure measurement. The regular atmospheric pressure is 14.7 psi. So your tire air pressure is half of what the pressure you put in your tire, which is pretty amazing. And of course, if you watch the weather map, you'll see high pressure and low pressure systems on the map, and that is what causes weather. Okay. Oh no, it's a cat meme. I can't believe it. It's one of the last cat memes of the year. The atmospheric pressure seems rather high today. Poor little kitty. Okay, so here's a bunch of gas laws. Will you need to know it? I'm going to say yeah for a quiz at the end of this unit here. So here's the three gas laws. We got Boyle's Law. Boyle's Law has to do with P and V. What's P and V? P is pressure, V is volume. So you'll see in a little bit what that is. Then comes Charles's Law, which is volume and temperature, so how they're related. And of course, the last one is Guy. His French. His name is Guy Louisac. And it's pressure and temperature. Okay, so let's go back. Then we have, let's go into all the gas laws. We got our Boyle's Law. And if you were taking notes, I'd be like, take out your notebooks and take these notes, and they'll be handy when you take your quiz. Boyle's Law is P1V1 equals P2V2. What does that mean? That means the pressure times the volume in one system equals the pressure times the volume in another system. What does that mean, Mr. G? Well, if we were doing math, which we're not, thank goodness, we'd be plugging in numbers here, and we do some algebra and some button pushing. But lucky for you, no math involved here. But what you do need to know is, as the pressure of the gas increases, the volume decreases. Now notice this little thing in parentheses here, if temperatures remain constant. Now we have the three things. We got the temperature, we got the pressure, we got the volume. So here we have temperature is constant. There's no T in the equation, so you ignore it. So what does that mean? It means the volume of the pressure and the volume and the pressure, they have inverse relationship, which means when the pressure goes up, the volume goes down, and vice versa. And here it is again. So pressure goes up, volume goes down. So at a constant temperature, the volume of the gas vary inversely with the pressure. As I said before, if you increase the pressure, the volume decreases. Why, might you ask? Well, back to the kinetic molecular theory. If you think about what's going on, you're squeezing the volume, which means there's more pressure because the particles are banging against each other, which is what pressure is. If you decrease the pressure, the volume will increase. So a larger volume means less pressure because there's more space, and they have space. You want a bigger volume for social distancing. So when these little molecules are socially distancing, the volume goes up because there's more space and less pressure and less chance for you to bump into another person that might have some contagious disease, just like the molecules bump into each other to share pressure. So that's what's going on. So pressure goes up, volume goes down, volume goes up, pressure goes down. They're inversely related. Now, a good way to remember that, and here's a whole bunch of cool demos, and I just love the cool demos. So here's a picture so you can see what's going on, and here's the Boyle's law. You have a container, you got the little gas in there, the volume is 1 liter, the pressure is 100 millimeters mercury. Does it matter? No, because we're not doing the math. If you squeeze that bottle half the size, now all that gas is scrunched up together and not enough social distancing going on over here. So their pressure increases. So the volume goes in half, the pressure doubles. Make sense? Yes. And actually, if we were in class, I would have you guys do this experiment. Maybe I'll do it for you for fun on my really cool Teach Talk, so you guys can see the pressure of the water bottle. When you squeeze the water bottles together, the volume gets smaller, the pressure gets bigger, which makes the top go boink. Now, of course, there's other ways of doing it. That's the one that I know you guys know how to do, but that's what happens to champagne, anything that has bubbles in it. Now, of course, there's also a Cartesian diver, which is also a cool demo that's really cool to do, where you squeeze it and the little thing goes up and down, which is very cool. I'll have to show that to you guys later. And, of course, putting a peep in a vacuum chamber is always the most fun thing for me to do, and that makes the peep expand because the pressure decreases, the volume of the peep increases. Same thing happens with a balloon, which I enjoy doing. And look, it looks a little bit like Miss Schwartz in there. So they're like, oh my goodness, look how big that's getting. And the answer is, you're right. And it's going to pop. Ow. So we got a practice question, see if you guys understand it. And of course, if I turn this into a Ed puzzle, this will be the question. What would you have to do with the pressure of a gas to reduce its volume to half? So if you reduce the volume in half, the pressure is going to increase by 2 times, which is the answer. So you double the pressure. So volume goes down, pressure goes up. Easy. So if you want to increase the volume 3 times, what do you do to the pressure? You decrease it by 3 times, which is what? Oh, that's not the answer. That's the next question. So you increase it by 3, decrease it by 3 times. Here's if you do it by 4 times. So what happens to the volume? If the pressure is increased by 4 times, the volume decreases by 4 times, or 1/4. Okay, so now we did pressure and volume. Now let's talk about temperature. How do we measure temperature? Well, obviously we use the thermometer, which is very popular to use nowadays. And of course, you can measure the temperature in Fahrenheit, which, of course, if you are American, we measure in Fahrenheit. In science class and the rest of the world, we measure in something called Celsius. And of course, there is another one. There's actually a whole bunch more, but there's another one, something called kelvins, which is going to be very important. Okay, if we did gas law calculations, which of course we don't have to, but I just want you to know about Kelvin, my friend Kelvin. So Kelvin, how do you figure out Kelvin? You do a little math. Kelvin is Celsius plus 273, and if you want to convert from Celsius to Kelvin or Kelvin Celsius, you subtract 273. That's how you do the math. But Mr. G, how do you convert Fahrenheit to Celsius? Do you really want to do that? I don't want to do that. Okay. So let's take a look at comparing them, and we saw in our guided reading measuring the 3 thermometers and comparing them. This one is Fahrenheit. So in Fahrenheit, here's our thermometer. We know that water freezes Fahrenheit at 32. We know that water boils at 212, and that's Fahrenheit. Now, of course, in science class, we don't use Fahrenheit. We use Celsius. So boiling point of water is 100 Celsius, and the freezing point is 0 Celsius. Now, let's talk about Kelvin just for a second. Kelvin is adding 273 to the Celsius number. So Kelvin, boiling point of water in Kelvin is 373, and the freezing point is 273. Mr. G, why does that matter? Well, the reason why is, let's follow this all the way down. 0 Kelvin. Now, you can have negative temperature in Celsius, below freezing, and you can have negative temperature in Fahrenheit also. So these you can have negatives. In Kelvin, you cannot have a negative. You have something called 0 Kelvin, which is, here on top, absolute 0. So absolute 0 is 0 Kelvin. That's what you need to know. And what happens at 0 Kelvin? Good question. Next slide. Well, let's think about solids, liquids, and gases, which my little guy is also learning too. Yay. So we have a gas. Okay, so we're talking about gas law. So let's take a gas, and we got this wild, crazy gas. They're bouncing around all over the place. And what happens is you cool it down, and you compress it, and now the gas molecules get closer together. So they're now they're not socially distancing. They are now a liquid. Okay, but the liquid still could be warm. So now you cool the liquid down even more, and it turns into a solid, which is freezing. So wait a minute, I kind of remember this freezing and melting and evaporation and condensation and sublimation and deposition business. Do you have to remember that? No, not really. But just look what happens when you cool it down. Here the molecules are bouncing around like crazy. Here they're moving, but not that much. And here they're a solid, and they're not moving at all. But technically they are moving. They may be sitting like you guys, if you're sitting in chairs in the classroom, you're sitting in a nice neat rows, but you're still breathing and wiggling and looking at your cell phones and texting. So you're still moving. You're not completely stationary, standing still, not moving at all like the chairs. Because something happens very cool. At absolute 0 is when 0 degrees Kelvin, and is the temperature when the particles stop moving. So as a gas, they're moving like crazy. As a solid, they're moving a lot less. And then as a but they're still moving a little bit. So solid, your table, knock, 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 even though it's a solid, the molecules are still moving. But at absolute zero, which is really, really, really cold, and just to give you an idea of how cold absolute zero is, how cold is absolute zero? Well, if you looked at the chart before, it's negative 273 Celsius and negative 400 degrees Fahrenheit. But how cold is that? Well, obviously, space is cold, right? I mean, obviously, those dudes in SpaceX, it's cold up there, but it's not 0 Kelvin in space. It's 4 degrees Kelvin in space. Absolute zero is colder than outer space. Really cold. And something really funky happens at absolute zero when they stop moving, and that's something called the Einstein-Bose condensate, which is super cool and interesting. It's the fourth state of matter, or just a fifth state of matter, because plasma is the fourth state of matter, but we're not going to worry about that. Okay, so there we go. We did that already. Now, let's go backwards. So we have a solid, we heat it up, it moves more. We heat up the liquid, it moves more. So we're increasing the temperature and decreasing the temperature. So let's just think about it for a second. If you decrease the temperature, it gets cold and it turns to a solid and it gets smaller. You increase the temperature, it goes to a liquid to a gas and it gets bigger. So, I think we can make an assumption with the gas laws with that. And here's an example. You heat up water, it turns to steam. It expands. The volume increases. So wait a minute. We have two things going on. We got temperature and volume. Interesting. And let's take a look at this. Winter versus summer. So now that the summer's ready and you're ready to go to the beach and drive around, you may notice your tires may change. So for you folks who are getting your driver's license, between winter and summer and winter, you need to check your air tire pressure. Why? Guess what? It has to do with temperature. So, in the winter, it's colder temperature. The molecules move slower. Your tire is underinflated. So sometimes in the winter, you have to add more gas to your tires. And then, of course, Mr. I would love this one. And then during the summer, what happens is the gas expands and now your tire's overinflated. And you don't want an overinflated tire when you're driving down to the shore because then your tire's going to explode. And that's not a good thing. So the best thing is to have a properly inflated tire where you have a full tread touching the road nice and evenly. The most tread touching the road so you get best traction. Now, of course, Mr. I would be glad to tell you that if your tire is underinflated, your wear pattern on your tire will be on the edges. And if you're overinflated, the wear on your tire will be in the center of your tire. And if your tire is properly inflated and, of course, rotated and balanced on a regular basis, you folks getting cars, you should know this, is that it gets full traction and it has nice even wear on your tires so you don't have to replace your tires as often. So, and of course, it's a lot safer on the road because all of this surface area is touching the road. So, wow, practical application of gas laws. Your tires.